Let's go through the prediction and correction just a little bit in the Kalman 1D case. Remember, we're going to assume that the state at time t, okay, is just a constant times whatever the state was at t minus 1 plus some noise that's added, some process noise, right? So the first thing we would like to do is we would like to know our estimate. What's our best guess at time t given everything t minus 1 when we've got this Gaussian model? Well, we're going to write this the following, right? If something is a Gaussian and I multiply it by a constant, what does that become? It becomes another Gaussian. Or another way of saying it, I have some variable that's distributed by a Gaussian, and I multiply that variable by a constant, I get a new value out, but it's also a Gaussian, right? And in fact, if you remember from probability, right, its mean is just going to be that constant times the previous mean. So that's what this equation here says. This equation says that if I have my belief about the mean at time t minus 1 after I've done all my work at t minus 1, and if I believe that my dynamics are multiplying the state at every time step by d, my belief before I take a measurement about what the new mean is just going to be d times that. That's what this equation at the bottom says here, right? Mu minus at time t, the predicted mean, is just d times the mean from what I had before, okay? Because d is my multiplier. All right, so you remember that when I multiply something by a constant and it's Gaussian, the mean just multiplies. But what about the variance, okay? So now we have to update the variance. There are two things that are going on. First of all, we're taking some previous variable and we're multiplying it by a constant. That variable had some sigma squared to it. And maybe you remember, if you have a Gaussian, when you multiply that by a constant, its variance goes up by the square of that constant. So just in the multiplication part, all right, whatever the variance was before is going to go up by now d squared. But wait, we're not done. We also added in some more noise when we took that step, right, of d squared. So that means the new variance before we take a measurement is made up of two components. It's d squared times whatever the variance was before, so that's written as d sigma t minus 1 plus squared. Sigma t minus 1 plus is the standard deviation. If it's squared, it's the variance of what we had at the end of t minus 1. We're multiplying everything by d, so we multiply that variance by d squared. That's what this term over here is. And then we added in some more noise because of uncertainty and of how the thing actually then moved. That is this d squared, okay? So even if we were multiplying by a 1, that is, even if we had no idea there was, you know, everything was just a 1, our variance would still grow because of the added uncertainty, all right? So the update of the mean and the update of the variance for the Kalman is written like this, all right?